pulsar problem. All right, so I will be honest, if you got this, then you are super badass. All right, I assigned this problem knowing full well that most of you are going to really struggle with this. Okay, so don't beat yourself up on this. All right, we're sort of working on starting to put in some more calculus-y style problems. All right, they will be coming with increasing regularity. All right, so let me see what we can get through here in the next, whatever, we have 7 minutes here. All right, so here we go. This is 11.2, number 8. All right, it says a pulsar is a rapidly rotating neutron star that emits a radio beam the way a lighthouse emits a beam. We receive a radio pulse for each rotation of the star, basically when that pulse is sort of directed towards the Earth. All right, the period t of rotation is found by measuring the time between the pulses. All right. The pulsar in the Crab Nebula has a period of rotation of 0.33 seconds. So we know that our period of rotation right now of this particular pulsar is 0.033 seconds. But notice, well, it says it's increasing. So the rate at which the thing is, rotating is changing. All right? So it tells us that the period is increasing at a rate of 1.26 times 10 to the negative fifth, and then it's stupid seconds per year. All right? We need to give that a name. So that's telling you the rate at which the period is increasing. So this is the rate at which the period is changing with respect to time. Follow? Questions with that? All right, now, question A wants to know what the angular acceleration is. Well, we don't have a lot to work with here, really. But the fact that this is a derivative, it's a rate at which our period is changing, leads me to believe that I probably want to use some calculus to solve this. All right, so the calculus definition of angular acceleration is the derivative of angular velocity with respect to time, right? Good? But the problem is we don't have any information about our angular velocity. We've got all this stupid information about the period. So we need to find a correlation. All right? So here's the trick. Okay? So what I know is this. I know the angular velocity is, it's basically that, right? Assuming that my angular velocity is constant, right? But if my angular velocity is not constant, then we could certainly figure this out, couldn't we? You guys agree with that? That I can find the rate at which my angular velocity is changing with respect to the period? Okay, so I always do this. This is the same as 2 pi times period to the negative 1, and then just use the exponent rule. Okay, so you end up getting negative 2 pi times t to the negative 2, which is the same as over t squared. Capital T. Capital T. Good? Yeah, sir.
Am I going to be tested on this in the near future?
It is possible that it could be on the AP test. Something like this. Yeah, it comes up.
So this would be like a harder level?
This would be a very hard, yeah. Yeah, this would be the one that most people don't get. And since the average score on the AP test is a 60, you just go, eh. But here's how you do it. All right? So are we all good up to here?
Yeah.
All right, so here's the trick then. So what I need to do is I need to come up with a way to rewrite this in terms of period. So d omega dt is the same as d omega d capital T times d capital T d little t. There's a name for that I don't remember. Somebody who's in a calc class, what's that called when you do that?
What?
when you split it up?
I don't know.
I mean, related rates problems are solved like this. It's a related rates problem is what this is, you guys. If you want to like tack a name onto it, this would be a related rates problem. That's all we're doing. Is it the potato problem? All right, so now at this point, it's kind of plug and chug. I've got an expression for dw dt, and I've got an expression for dt dt. So I don't have enough room. So here we go. So our alpha is dw dt, which is negative 2 pi over t squared. Remember, t was 0.033 seconds. Don't forget to square it. So that's this times dt dt, which is this, 1.26 times 10 to the negative fifth seconds per year. And then you got to do one other thing before you're done, which is we got seconds and years in the same problem. So you then just got to multiply by a conversion factor to get everything to seconds. So times, let's see, 1 year is 365 days. And then 1 day is 864 or 86,400 seconds. Just 24 times 3,600. And that gives you the answer. Questions with that, you guys? Sorry, kind of a kick in the teeth on the first day back after break. All right, so real quick, I know the bell's about to ring here. So I have no